Okay, well, let's go ahead and get started. Really excited to be hosting this webinar today. There's been a lot of great work that's gone in behind this, so let's jump in. On behalf of the team, thank you everyone for attending. Today, we're going to be covering with our partners over at AWS, optimizing LLM inference with Ray, vLLM, Neuron, and EKS. By way of introduction, I'm Matt Connor, product manager at Anyscale. I'll be joined today by my colleague Akshay, who's one of the engineering managers at Anyscale responsible for serving, as well as our partners over at AWS, Vara and Art. They will introduce themselves as they come up, but in the interest of time, we'll keep things moving here. For an agenda today, a couple of quick announcements we'd like to start with, a few really exciting events coming up over the next few weeks that we want to make everyone on the call aware of. We'll then jump in with a very brief Ray and Anyscale introduction before handing off to discuss AI and LLM trends more broadly. Akshay will do a bit of a deep dive into vLLM and Ray Serve before Vara will jump in with a demo, bringing everything we talk about to life. And then time pending, we'll open it up for some questions at the end here. So this is what we're planning to cover today. Now, first on the announcement side, we have coming up at the end of the month here our annual Ray Summit. This is our gathering of about 1,000 plus ML practitioners and builders that we're really excited about. So September 30th to October 2nd in San Francisco. There's a full day training. We have a number of very exciting speakers, including Mira Murati, the OpenAI CTO, attending. We also have a very specific vLLM track at Ray Summit this year. So for those of you on this call learning about optimizing LLM inference, a lot of the key contributors of that project will be at Ray Summit, and about 10 talks dedicated to vLLM and all the great work going on there. So be sure to check this out. We can offer everyone who's on this call a 15% off code. We'll share these materials after, but go ahead to raysummit.anyscale.com and you can go ahead and register. Second announcement I wanted to share is a little further out, but our teams will also be at reInvent coming up in early December. So Art here, as well as our head of training, Camille, and one of our in-house machine learning engineering experts will be there for training. We'd love to see you there. So if you're making plans to be at reInvent, please register. And I think we have a phenomenal program put together to help train and share more about our joint solution and how it's powering LLM and Gen AI applications and more. So that's it for a couple of announcements. We'll circle back to these at the end. As I said, we'll share these materials later on. So let's go ahead and do a very brief Ray and Anyscale introduction. By way of introduction, Anyscale, the company, we are the creators and maintainers of Ray, which is an open source compute project that actually came out of research done at the UC Berkeley RISE Lab. Ray was created as our co-founders were trying to figure out how to scale their AI workloads, both training, serving, and beyond. And so even back in 2016, they were running into issues doing so and created Ray to address that. Obviously, now here in 2024, you're going to hear about some of the big AI trends, and so very well positioned for what we've seen with this new era of generative AI. Anyscale, the company, was founded in 2019 to commercialize that project and provides a fully managed platform to make scaling AI seamless, easy, with the very best performance we can. Today, Ray has been widely adopted and is the standard for running AI workloads at scale. At the same point in its history, it's seen tremendous adoption compared to other very popular open source projects, and a number of huge organizations rely on Ray for their AI workloads, ranging from OpenAI, who trained GPT with Ray, to Uber, Spotify, Netflix, Apple, Coinbase, and more that are all building Ray-based AI platforms. So really exciting to see the adoption and where we are today. Last comments from me, and then we'll jump into the meat of the program. What does Anyscale do on top of this? Well, Anyscale provides a managed Ray platform where we've really focused on 4 key parts of enhancing the Ray experience. First is optimizations we've made to Ray to make it more performant, reliable, scalable, and cost-efficient. The second is a suite of developer tooling to make it very easy to build applications with Ray, ranging from data processing to training to LLM inferencing. We've added security and governance to meet enterprise requirements, and then seamless integrations into an ecosystem of MLOps tools to make it a fully configurable, powerful AI platform. So that's it for me. I'm going to hand it over to my colleague here, Art, who will shed some light on what are some of the major trends we're seeing around LLM inference broadly, and where are things going.
Thank you, Matt. Hi, folks. My name is Art Sedighi, and I am a solutions architect with AWS GenAI team. I wanted to start by reviewing the latest trends that are propelling the flywheel forward with GenAI. Customers are driving AI innovation at an accelerating pace in order to keep up with application use cases and demand. Possibly the hottest topic in deep learning is the explosive growth of large models based on transformer architectures. In the recent years, these models gained popularity due to their pseudo accuracy and scaling properties, with some customers training trillion parameter language and computer vision models. Another critical enabler is the self-supervised training approach, which has helped data scientists tap into the vast wealth of unstructured and unlabeled knowledge available online. This in turn helps to boost model accuracy and supports training these large language models with billions and trillions of parameters. In the last element, but still critical, is that the state-of-the-art models such as Stable Diffusion, OTP Bloom, OpenFold are becoming readily available via open source contributions. These open source models help increase adoption of new model architecture and often enable data scientists to improve model efficiency. Just as a note, when we say these AI models are getting bigger, we mean exponentially bigger. As shown here, the number of parameters in machine learning models have been growing at a staggering pace, roughly about 10x a year, and even faster for some specific model types. This curve is just getting steeper. These models are demonstrating new emerging capabilities that are unlocking even more applications. From an applications point of view, what are some of these applications and use cases? There are plenty of examples, but I'm just going to go through some of them here. Generating new piece of original content, such as short stories, jokes, arts, songs, images. Helps you with automatic code recommendations to accelerate application development. Getting a brief summary of articles, books, and documents. Writing assistant to rephrase a text you wrote or reshape a message in a particular tone. Chatbot and virtual assistants to enhance user experience for your customers. Allows you to search, find, and synthesize information from large corpus of data that's available on the internet. Image classification of 1 million plus SKUs, image generation, some wild images. These are just some use cases, but regardless of the use case, one thing that these use cases all agree on is the need to lower the cost of running these models in production. But training and deploying these large models to power these use cases is far from easy. There are several challenges and trade-offs that machine learning developers and engineers face daily. Developers are trading performance and cost. If you want to train these models quickly, you need to deploy them to a cluster of GPUs, but that turns out to be very expensive. You could use less expensive hardware that, then the training time can take months or even longer. This is where purpose-built accelerators come to the rescue, right? We have purpose-built Trainium and Inferentia for these ultra-large GenAI models and large language models. This allows developers not to have to make these trade-offs. And these Trainium and Inferentia instances allow developers to focus on their applications and still get the best performance for training and the best inference performance possible. For inference, which is the topic of this webinar, the goal is to increase inference throughput. We conducted a benchmark of a BERT model where we wanted to hit 10 million inferences per hour. If we deployed this model to a GPU-based instance, it would take about 8 GPUs to achieve this performance. But the same workload will just take 4 Inferentia 2 instances, cutting the required instances by half, And because we're using more efficient hardware and fewer of them, we also cut out the power consumption. Overall, we were able to reduce the inference cost by 65%. Putting this all together, we have innovated across accelerators, server types, data centers, and we're binding them together with the right software services. We have been able to build the largest clusters to date. We have integrated Trainium with a wide range of AWS services that you are potentially familiar with. This includes standard storage and networking services such as S3, FSX, or EFA, orchestration services such as EKS, ECS, parallel clusters, or batch. In addition, deep learning specific capabilities such as the deep learning AMI and the deep learning containers also support Trainium and Inferentia instances. This allows you to get up to speed and get started very quickly. With that, I will hand it to my colleague, Akshay, to speak about Anyscale, RayServe, and vLLM. Akshay, I'll stop sharing and you can take over, please.
Yeah, thanks, Art. Cool. Yeah, so let's talk about vLLM and RayServe. So vLLM has been growing in popularity massively in the last year or so. You can see the GitHub, it's already reached 17,000 GitHub stars, and also like popular in many companies as their inference engine. So what was the goal that vLLM started with? They wanted to build the easiest and fastest open source engine for LLM inferencing. And they started with some simple ideas around batching and like doing optimized scheduling of requests that come in, as well as better caching of requests. So there's a lot of data that's computed across many decoding steps that happen during an LLM inference. And they built some novel innovations around caching data across these multiple decoding steps. So since then, they've had two major patterns of usage. There is an offline API. So this is for offline batched inference, where people want to infer on, let's say, your entire corpus of documents offline. And vLLM has a lot of inference optimizations around that, as well as an API server for online inference. So this is where you're using it in real time. These are some of the features. And vLLM at this point has grown and become like this big project that originally started out of the Rice lab in Berkeley, but now there's been multiple contributions from many companies across the board. Anyscale as well is one of the major contributors to vLLM, contributing many new inference optimizations like speculative decoding. But there's a lot of other companies with a lot of interest, and part of it is because vLLM is so easy to use, extend, and not closed source like some other engines like TensorRT LLM. So today it supports a wide range of model and different model architectures. It has Llama, Mixtral, all of your popular open source models, as well as vision language models like Lava, Pixtral that just came out recently. So new architectures are added very quickly within days of announcement. There's a wide range of hardware support as well, which is another reason why it's so popular, because of its extensibility. So it supports NVIDIA GPUs, but also AMD, AWS, Inferentia, and Trainium, as well as Intel and Intel CPUs, and the new stuff that Intel is launching around Habana processing units as well. And then it has a wide range of inference optimization. So you can set up tensor parallelism, quantization, which is popularly used to reduce model size, prefix caching, serving multiple fine-tuned models behind the same endpoint, and spec decoding, which is really used for speeding up inference times by using a smaller draft model to predict some tokens. So all of these combined are very easy to set up behind one simple vLLM API for any of these popular open source models on any type of hardware. So get RayServe. So RayServe was originally, we looked at what are the real problems to solve in ML serving. So some of the big problems that exist today, and these were relevant 2 or 3 years ago, these are even more relevant now, is there is long lead times to go from development to production. So people would train their models offline using their notebooks or whatever bespoke setup. And then they would use different kinds of hardware and infrastructure to do that. And then they would have to figure out how to translate their code to run online and how you get the models over from your data scientists to the software engineers who are developing your web applications. And then it's expensive to build and maintain many different models in the same application. So if you are building a recommendation system, for example, it's most likely a combination of 2 or 3 different models that are chained together. And they all might have their own like memory and resource requirements, like different GPU, different CPU requirements. But there's no good patterns for deploying these while maintaining low operational overhead. Like people either set it up as separate microservices, as the SageMaker kind of route, where you can scale these independently, but now you have a lot of operational overhead of maintaining all these services, or you can set up a monolith, but then you're not scaling as well because you're not utilizing your GPUs and CPUs the best you can. The third one is you want to have a very extensible framework. So a lot of frameworks like TensorFlow serving or PyTorch serving were really limited in like the libraries they can support, or even Triton was very limited in what types of inference engines you can run. And then you also want to be able to run on any type of hardware, GPUs, new hardware coming out from AWS or other vendors. So this is where RayServe came in, where the idea was build something that is high performance, flexible, and super easy to use. So RayServe is a scalable Python framework to put ML applications in production in Python with just a few lines of code change. So you add a couple of annotations to your Python code and you're good to go. And you can mix and match many different models and build a complex ML application where each of these models can scale independently, but everything is behind one single service. So there's features in RayServe called model composition, model multiplexing, fractional GPUs. All of these allow you to get the most out of your hardware and deploy these more complex ML applications that are more than just one single model behind an endpoint. And then it's extensible by design. So you can bring in any framework like PyTorch, TensorFlow, any optimization engine. Like you can run vLLM, you could run TGI, you could run TensorRT LLM as well, all behind one single pane of glass. So this was the big motivation behind RayServe, and a lot of people deploy vLLM with RayServe to get that complete production readiness that RayServe offers with the optimizations that vLLM has. Now I'll hand it off to Vara to do a quick demo.
Thanks, Akshay. Let me share my screen. All right. Hi, everyone. My name is Vara Bonthu. I'm a principal open source specialist architect working with AWS. And you heard from Akshay and you heard from Art and Matthew as well. There are a number of ways that you can deploy LLMs today, inference on various platforms. And within AWS, you have SageMaker, Bedrock, and even Amazon EKS. For the customers who actually standardized their workloads running data and ML workloads running on Kubernetes. And this demo is for you, where we will show you how easy it is to actually deploy large language models such as Llama 3 8B model on Amazon EKS using Ray and Neuron. And today specifically, we will be using Inferentia instances. So before we get into looking at the demo, let's talk about some of the key components that you need to deploy any model on Amazon EKS. And let's talk about some of the plugins. Right. As you see on the slide on the left-hand side, you have Amazon EKS control plane that is fully managed by AWS. So once you deploy EKS cluster, that's the first step that you want to deploy an EKS cluster. And then to scale up the nodes, and you will use Carpenter or Cluster Autoscaler, where it will create necessary nodes for you to deploy the workloads. But actually to deploy LLM inference on neuron instances such as Inf2 instances or Trainium instances, you need a couple of plugins, right? So let's talk about some of those things. And to start with, EKS Army with the neuron drivers. So when you want to deploy your workloads, you need to make sure that you use the right AMI. Currently, the neuron drivers are available as a part of Amazon Linux 2, which is what you see in this. And it comes with the drivers like AWS Neuronix drivers. So once you use AMI, and you should be ready to start working and deploying the models or even training the models. And then step 2, to expose some of these neuron accelerators, such as from Inf2 instances, even Trainium instances to Kubernetes API server, you need a neuron device plugin to be deployed. It's a daemon set, and you can use kubectl manifest to apply it, or you can use some of the Helm charts that we are planning to publish it soon. And that's going to run on every single Trainium or Inferentia instances that will make sure that these resources are available to Kubernetes API server to schedule your workloads. And then the next plugin is the Neuron Scheduler extension. As a part of the Neuron Scheduler extension, this is really useful when you are using a larger instances with multiple neuron devices and cores are available, where you are only requesting fewer number of devices. Say, for example, you want to deploy multiple replicas of the same model within the bigger instance, and you want the scheduler to actually schedule your workload. It ensures that your scheduling of those devices happens in a contiguous manner based on the model that Trainium supports as well as Inferentia supports. And then moving on to neuron problem detector. This is one of the common things, and you might have heard already, even the GPUs or even neuron instances. Sometimes there are hardware failures while you're doing training or inference. What you really need is, and you want the instance to be identify those hardware failures, and then restart the node and redeploy the workloads. And so neuron problem detector, the add-on that we, once you deploy as a daemon set, that identifies it and replaces the node for you. And then finally, neuron monitor daemon set. This is useful to actually export all your metrics, such as neuron metrics, to either Prometheus or CloudWatch metrics. So that's all you need in terms of the plugins. Once you have EKS cluster and all the plugins, you're ready to deploy your workloads. So let's talk about the architecture before we go into the demo itself. This architecture, it's deploying Llama 3 8B, 8 billion parameter inference on EKS using Ray, vLLM, and Inferentia. It's a great combination. Ray is very popular among a lot of the users and the customers, and it helps you it simplifies the whole journey of deploying your workloads on Kubernetes. And then with the combination of vLLM, and that's a powerful backend engine that Akshay mentioned before, which improves the performance of your inference in terms of batching and requests. We can take a look at that once you go through this architecture. But in this architecture, as you see, we have an EKS cluster, and I have Carpenter Autoscaler, a very powerful autoscaler. I highly recommend for customers who are using deploying your workload, especially the inference workloads. With the Ray, it always comes with the Ray head pod and the worker pod. So when you use the Ray service API, it creates a Ray cluster and also creates an AM service so that you can interact with the service and work with the workloads. So we can look at the actual spec of how to deploy this, but in summary, the virtual assistant, as you see on the left-hand side, where the users interact with the network load balancer or application load balancer, sends a request to ingress controllers like Nginx, and that reaches to the individual nodes where the model is deployed. But here I'm using Inf2 8x large. As you can see, there are 2 instances. That means you can scale horizontally based on the auto-scaling capabilities that Ray provides. That can be any metric that you choose, that based on that metric. an array creates multiple actors, and you scale your workloads even within the node, even across the nodes. So with Inf2 8x large, we only have one Inferentia chip, and we have an accelerator memory of 32 GB. But to load the Llama 3 8B instruct models, I think we need somewhere around 22 GB of accelerator memory that fits into a single neuron device. And each neuron device comes with the 2 neuron cores. So we are using a tensor parallelism of 2 to ensure model loads into neuron cores. And then you can also see the neuron device plugin, which is running as a daemon set on every single instance. So the model can be pulled from Hugging Face, but in this example, we are pulling from Hugging Face, but you can also use a model stored in your local disk and model stored in S3 or even S3 mount point, various approaches. And Amazon ECR is used to actually store your container images. Like today, we are pulling an image from ECR that contains all the necessary plugins and everything. That's pretty much an end-to-end. It's a simple configuration, and you can deploy all the models which are supported today with the Neuron for the inference using either Inf2 instances, even Trainium instances. Say, for example, when you want to look at deploying Llama 3.1 405B model, which is like a distributed inference model, you can look at using Trainium 32x large across multiple nodes as well. But then the question is how to deploy, right? So we want to run all of these workloads on EKS, and do you have any patterns or examples that we can go ahead? But this is at AWS, we created this data on EKS initiative, which is an open source solution. You get all the patterns under Gen AI. When you click on Explore Gen AI, you have number of training and inference patterns available. So we're going to look at the key pattern that we are going to see a demo now. Right, let's get started with the demo. So for the sake of deployment, so the actual deployment of EKS cluster will take, let me go into the code. This is the repo I mentioned about, and these are some of Terraform templates. But if you are using any infrastructure as a code, you can use this as a reference. But if you are using Terraform, it makes it a lot easier. So there is only one command here, install.sh. You go to Trainium Inferentia path under the repo. Once you clone the repo, you go to the AAML Trainium Inferentia and run install.sh. That will take nearly around 17 to 18 minutes. That will create EKS cluster. It deploys all the necessary plugins, including Carpenter and so on. So once that is done, then the next step is to go and deploy your actual workloads. Because with the Ray, there's a kuberay operator available, and this module also deploys the kuberay operator. And all those plugins are available. The code is within the add-ons.df. Right, so now let's get into the actual deployment Ray YAML file. This is where you are interested in. So once you have EKS cluster running, kuberay operator running, and all the neuron device plugins are running with that previous step, and the next thing you do is to create a manifest. And that manifest, we have an example here under generative AI, vLLM Ray Serve Inf2. But before we go into the manifest, this is the Docker file where I'm using Ray project to create a custom Docker file with all the necessary packages. Sometimes you want to bring your own packages, some NeuronX packages, and so on. That's pretty much. Once the container is ready, you push it to the ECR, and we will use that container image within the Ray Serve spec. Right, so this is the vLLM Ray Serve deployment file. I have deployed it, but we'll take a look at it in a minute. In this, I'm just creating a dedicated namespace, and I'm creating a config map, and config map contains that serving script. The serving script is OpenAI API compatible. So basically, pretty much you can use the streaming way of serving that model. This loads the model and inference the model pretty much. That's good. And this is the Ray Serve API spec, Ray Service API spec that you're interested in. In this case, we're using the same namespace. And the key configurations here, I'm pulling this model from Hugging Face, which is, in this case, you need to get an approval from Llama 3, the license and so on through Hugging Face. Once you are enabled to pull that model, you can use that. But this model does not require, so I'm using some open source model from Hugging Face. We're using tensor parallelism. You can set all these parameters based on your model size and so on. And this is where the auto-scaling configuration comes into, number of replicas that you want. These are the active replicas. And this is the configuration for the neuron cores. Because I'm using inf2 8x large, I only specify neuron cores 2 per actor, and I need 2 CPUs, but that can be further customized. And this is the image where we specified my head pod is using, and even the worker pod is using. The image does not contain this serving script itself. That is coming from the config map that we mentioned before. So we have set up other configurations, but the key configuration that I want to highlight here is the neuron resources here that you see in line number 267. For the worker group spec, this is where you see how many number of workers that you want to spin up. And sometimes one worker can run one replica, but the larger instances, you can run multiple replicas within one worker. But each worker, it's configuring as neuron cluster 2. This ensures that horizontal scaling of number of nodes happens in the expected manner. So we are also using custom neuron scheduler that will ensure scheduling the pod. And this is the key configuration to run on inf2 instance, because I'm aiming at inf2 8x large, which is a smaller instance with one neuron core. So I'm using CPU and memory is aligned to that, because using these requests and Carpenter actually kicks in. Is my video off? Right, sorry, I'm a bit late on that. Right, okay. So using the Carpenter looks at these CPU and memory requirements and then identifies the right instance and spins up. So for example, if I wanted to spin up a larger instance, and if I can like inf2 48x large, I just need to change my CPU and memory to the larger based on that instance capacity, and Carpenter spins up the right instance for us. So in these cases, you can have multiple replicas running within the same 48x large instance, because inf2 48x large, I think, provides 6 neuron cores, but I need to double check again. But inf2 8x large has only 1 neuron core. So that's pretty much, this is the only configuration. But to deploy this, all that you will be doing is kubectl apply on that vLLM racer deployment. That's the only command. Once you run that command, you should see the model. And so as you can see here, I already ran that deployment and it's under vLLM. I have one head pod running and one worker pod running. And the head pod, within the head pod, and the worker pod scales horizontally based on the request that you're sending, because we have auto scaling enabled for that. But to send an inference request, I have also created OpenAI Web UI, which is very powerful. Web UI, rich Web UI connects to this, our service, and then showcases, we can take a look at how it interacts with the service model and gets a response back. But let's look at the Ray dashboards, right? So once this creates one for head pod, one for service pod, worker pod, and then it also creates a bunch of services, one for a head service. The head service exposes that Ray dashboard, which is here, 86.5. And the actual model is exposed through the port 8000, which is part of the specific service that you see here, vLLM Llama 3 into serve service. Right, so I already done that. So let's take a look at Ray dashboard. So this is the Ray dashboard. You can see the deployment, vLLM deployment that we deployed. So when I click on the deployment, that will take you to that deployment, specific deployment. And Racer shows the deployment here with one replica. Let's go back to that. That's the one replica is running. And then you can also see the individual actors. So now this model, we looked at, this model is available under, the service name is vLLM Llama 3 Inf2 service, and Open Web UI, the deployment that we created, that is also part of that code that actually interacts with this service and does inference. So let's look at the actual demo here. So let's start with the new chat. And what you see here is a localhost 8080 is a port forward on the Open Web UI service. and the model is exposed here. So this connects to the model that we deployed on EKS. So you can simply select that model. This is the model. Once you select the model, you can pretty much ask what is generative AI and explain. So you can see the streaming output. It's basically going to hitting our inference server into XLarge and getting the response back. But if you send hundreds of requests, and autoscaling kicks in and start showing some of these the response back. And it also, I think we can take a look at the autoscaling now. One way to do is, while this response is coming through, we have a bunch of scripts within vLLM Racer. One script is an open client. So if I do, so we only have one replica at the moment that we looked at as a part of the Ray dashboard actor. Go to the serve, one replica, but the one way to test is putting some stress on it, sending multiple requests so that you should see more replicas showing up as well. Before I run this command, and I think we need to do a port forward on a specific service, which is 8000. Because that client is using this specific service. So the port forward is done. Going back and running this. So I'm running multiple, just sending multiple requests to open client to see the behavior. Probably take a couple of minutes. Show up. So I've sent a number of requests so far, and we should, and the array should show the replicas, and probably take a couple of minutes before it actually identifies that. And then we should start seeing some pending replicas to load. But then while that is coming up, let's go back to the service again with the code. So, right, so we looked at Open Web UI as well. And the way the Open Web UI, again, we containerize the solution. So that interacts with the vLLM service that we deployed that's running on Inf2 instance. But one thing probably would be nice to see is, let me show you guys. The instance itself. So here, what you see here is the neuron top coming. So if you want to, this is the node that we are using as a part of this deployment. And Neuron LS will show you how many neuron devices and cores are running. And Neuron top will show you the usage of the accelerator memory. Say, for example, we want to send some requests now. So you should see some of the green thing lit up in both the places. That's basically sending inference, and the accelerator memory is used and getting the response back. There's a usage of 95% there. So yeah, that's pretty much what I wanted to show today. As you can see here, there's a couple of steps that you can deploy and and then start influencing the workloads on EKS. So with that, I will open up for the questions, and Matthew, bringing you back on.
Sounds good. Thanks, Vara. I see a handful of questions here, so we'll go through a number of them and then wrap up. So first, we had a question on doing batch inference for text embedding models. Perhaps Akshay, do you want to address if we can do batch inference for text embedding models as well?
Yeah, absolutely. So the typical library that's used for batch inference is Raydata, and with Raydata, you can set up again, like these heterogeneous workloads on a very large scale of data set offline. And it has a lot of connectors to data catalogs as well, and it can run any models under the hood. So that's the typical pattern. So even when you set up batch inference with vLLM as the engine, you would set it up with Raydata orchestrating the vLLM engines and preparing data to be processed.
Great, thank you. Next question on a book or online course to learn RayServe. I'll give a shameless plug for Ray Summit again and some of the training going on at that event. I would say maybe perhaps some of the best resources are the documentation around RayServe. So if you go to ray.io and take a look at some of the docs, there's some really good tutorials that walk through RayServe in significant detail and can get you started. We are hosting a number of different training events, so keep an eye out on that as well. Sharing the code base. I think, will we be able to do that, Vara? Can we share some of the things that you put together today? Oh, I think you're muted, Vara. Sorry.
Sure. So let me send a link here to all the participants.
Great.
That's a link where the code is available, and the link where, yeah. So if you want to deploy, whether it's a training or inference, yeah, you have pretty much all the examples in the code in there.
Awesome. Thank you. There was a question on, do we need a separate head node for each model deployment? So Akshay, you were talking about model multiplexing and deploying multiple models at once. Can you talk a little bit more about any requirements around multiple head nodes or how that works?
Yeah, so with RayServe, you can set up one service with many different models. So each service requires one head node. So you can have one head node shared across many different models that you orchestrate in one service.
Great. A next question on sort of monitoring utilization. I think you touched on that, Vara, but some questions on perhaps being able to forward that information to something like Prometheus. So can you talk a little bit about that?
Yeah, sure. So currently, like we talked about, Neuron Monitor, that's running as a daemon set or the deployment, and that actually exposes the metrics to both CloudWatch as well as Prometheus as well. So we can visualize those metrics. And on top of that, you have this Neuron LS and Neuron Top, which I showed as a part of the demo. You can look at individual monitoring, but so we are planning to publish a little bit more observability around the example I shared. So you will have all the Grafana dashboards which visualizes those metrics.
Great. And then there was a question on the tool that you were using to access the pods when you deployed your Kubernetes cluster in Kubernetes. Can you comment on what that was?
Yeah, sure. So to simplify this, accessing the Kubernetes, I'm using Lens. It's not an open source tool, just to be aware. So that will give you, like, if you want to manage multiple Kubernetes clusters, it makes it easy to, access.
Great. And then we'll take one more and then have some final comments. There's a clarification question on if we need a different head node for serving text generation and image generation models, Akshay. My understanding, I'll jump in and give my answer, is no, you can have one head node, and then you'll just have multiple replicas deployed that can serve different models, but one head node, not a different head node.
Yeah.
Great. So with that, I'm just going to share my screen one last time here. Again, plug for Ray Summit. We have an enormous slate of announcements that are coming as part of Ray Summit, ranging from new functionality to improve performance of Ray, a capability we've internally, I'll tease it here, that we've been calling accelerated DAGs to really boost performance. There's a whole host of other announcements that we are incredibly excited to share that the team's been heads down working on over the past couple months. So we'd love to see you there firsthand to hear all of the exciting updates and things we've been up to. And then also another plug again for reInvent. So for those of you planning to make their way out to Las Vegas in early December, would love to see you there. Amazing opportunity to see us and do some training and meet Art and Camille and Marwan and the team. So I think that wraps it up. Be on the lookout for another webinar coming soon, and hope to see you at some of these events. Thank you, Akshay, Art, Vara, for all your help, and appreciate everyone joining.
Thank you very much.
Thank
Thank you
you.
all.
Thank you.